Hello, welcome everybody to Geo-Wednesday. It's a pleasure to have today's speaker here, Joe LaCasce, a colleague of mine, professor in meteorology / oceanography. Who is Joe? Who doesn't know Joe yet? So Joe is an oceanographer. He did his PhD in physical oceanography at the MIT US in 1996. 2002, he came over, moved to Norway, first as a senior scientist at the Norwegian Meteorological Institute in Oslo. And then in 2007, Joe got his professorship at the University of Oslo in 2007. Beside that, Joe also holds an adjunct scientist position at the Woods Hole Oceanography Institute in US since 2004. What is Joe working on? So Joe's interest is on large-scale dynamics in the atmosphere and the ocean, turbulence, Lagrangian statistics, but he also started working on paleo-oceanography, on the topography effects on the circulation, among other things. So privately, Joe, he just told me I should say, plays a saxophone. He loves to play music, and many of you have heard him before. He likes to cycle, and he also likes to sail. And today, he will give us a physical oceanography talk, a Scandinavian Eventyr, adventure in English. And a pleasure to have you here. We will have up to 45 minutes. If you want to ask him a question, please send me an email, and then I can ask the question for you. Thanks a lot, Joe, and the stage is yours.
All right, thank you, Kiki. Okay, so I'm going to talk about something you might not have known about. One of them is physical oceanography. That's really my field. And also the Scandinavian contributions to that, which were very important. So if we start with physical oceanography, so physical oceanography is really the study of the physics of the ocean. So that's where I come from originally. I was a physicist. But instead of studying one of the typical areas of physics, nuclear physics or astrophysics, I got interested in the physics of the ocean. It's a little more nearby, so it's something that is easier to identify with. And physical oceanography is itself is divided up into two different areas. One is descriptive, and the other one is dynamical. And I'm a dynamicist, but the descriptive part is equally important, and it came first. So I'll explain how this works. Okay, the interest in the ocean began really early, before the 1600s, because people were interested in exploring. And the way to explore, if you lived in Scandinavia or you lived in Europe, was via the sea. So to sail to different countries. And this is a map of the different sail routes that were made before 1600. And you see that there were trips from Portugal and Spain to the South America, also England to North America. Of course, Scandinavia is not shown here, but the Vikings sailed over there as well. So we've had an intense relationship with the ocean for a long time because it was important to know how it behaved if you were going to sail on it for months and months. Now, at some point, people began to map out the currents. So this is what we call descriptive oceanography, where you're plotting out the currents. And an example that's here. Can they see my mouse? Does that work? If I put a mouse? Okay. Anyway, on the left side here is a map that Benjamin Franklin made back in 1775 of the Gulf Stream. And the Gulf Stream is an intense current in the western Atlantic that flows up along the coast of North America. And sailors knew back at this point that if you sailed in the Gulf Stream with speeds up to a meter a second, that you could get to Europe faster than you could if you went south of there. And likewise, if you came back from Europe, it made more sense to sail south of there and then to come into the across here, the Florida Straits, and then sail up along the coast that way because you were sailing with the currents. If you sailed against them, it was very slow, and we'll come back to that in a minute. This is another map on the right, made in 1845, of different currents that were done. Okay, so now we come to some of the early oceanographic studies, and of course none of these were done by oceanographers because there were no oceanographers back in these times. So James Rennell is an early important figure, not a Scandinavian, he was a Brit, and he surveyed with the Royal Navy. He wrote a book called Currents of the Atlantic Ocean, where he talked about the different currents that they were able to map out back then. This is remarkable that they were able to do this because with a sailing ship, the progress is relatively slow and the sampling is very localized, very spotty. But he was able to draw together evidence from different ship campaigns and to make a description of what the currents look like. And Reynolds believed that the currents, and this is another thing that comes up quite often in this talk, is that what drives the currents? Why is there a Gulf Stream? And Reynolds believed that the primary reason for the currents was the winds. So the winds were the major driving force in the ocean. Okay. Then comes Alexander von Humboldt, who's well known in a variety of different fields. And Humboldt also sailed across to the New World, to South America, and also to North America. On an expedition and was particularly interested in just about everything, but interested particularly in cataloging species and so forth. And he published over 21 years these different travels that he made. So he was, among other things, he was one of the first to describe human-induced climate change. Humboldt believed that all systems on the planet were holistically linked. Something that we now think of as the Gaia idea, where you have an intimate interaction between atmosphere and the ocean, but also vegetation and human beings. And he believed that humans could actually affect the climate, which was obviously correct. But in addition to that, he mapped the Gulf Stream and speculated about how the currents were driven. So he also believed that winds were a primary driving force for instance, for the Gulf Stream. What he thought was that the trade winds, which blow from east to west at the equator, force the water across the equator to pile up in the Gulf of Mexico. And so this excess water in the Gulf of Mexico then spilled out into the Florida Straits, and that was the reason why we have a Gulf Stream. Okay, not correct, but it's a good idea. But another interesting idea that he talked about was that if you're at the equator and you measure the surface of the water, and I've been there, the surface is very warm. So it's typical to have temperatures in excess of 30 degrees right at the equator. But if you measure deeper down, when you go further down, then you start to sample water which is colder. And Humboldt said this colder water is probably coming from the poles. So he said that what was happening likely was that you had a deep circulation of dense water, colder water coming from the poles and then upwelling at the equator. Very influential ideas. Okay. Now in meteorology, they already had the concept of the Hadley circulation. This was George Hadley, was a British scientist. And this is on the left here. And what Hadley said in the atmosphere is that you have warming at the equator that causes convection and upward vertical motion at the equator, and then that air moves poleward where it descends and then returns at the surface back towards the equator. So that's where these arrows are, the surface flow coming back towards the equator. It's also a little more complicated than this. Okay, so now we know that we have several cells. There's a ferrule cell as well. But anyway, this idea came out very early and was very influential. So in the 1800s, Lentz published this picture about the oceanic overturning circulation, and it's very similar. So this is if you look at this is the North Pole on the right here, the South Pole on the left. You have cold temperatures. We're going to come back to this, but you have cold temperatures in the north, and that causes convection in the opposite direction. So one way to think about the ocean often is that it's the atmosphere upside down. In fact, we even measure it that way. In the atmosphere, z equals 0 is the surface, and then you go up positive values from there. We say z equals 0 is the top and goes to negative values below. Anyway, convection happens at the high latitudes. You get sinking here, and then just as Humboldt suggested, you have flow at depth towards the equator, and then you have upwelling at the equator. So vertical motion happens at the equator, and then it moves north at the surface. Okay, so we have an oceanic overturning circulation. Okay, now, so there's two ideas going around here. There's, you have wind-driven currents, and you also have what we now call it density-driven or buoyancy-driven currents, forced by the large-scale heating and cooling at the surface. This led to a debate in the early 1870s, and this was a vicious debate, okay? There was Carpenter, two scientists, Carpenter and Kroll. So this became famous as the Carpenter-Kroll debate. People don't talk about this so much anymore because when we moved on to dynamics, then some of these ideas weren't as important. But back then, this was a big deal, and it was vicious, okay? Again, neither one of these two are oceanographers. Carpenter was a neurologist and a zoologist, okay? We're going to see an example later on of another oceanographer who also had a background in neurology. Carpenter was on different ocean surveys, a couple of famous expeditions on the British vessels, the HMS Challenger and the HMS Lightning. And these expeditions went over years and, again, sampling the currents, but also visiting different countries and looking at species and so forth. And Carpenter believed the density-driven, the theory of the density-driven overturning. In addition, he said that Europe, so Northwest Europe, was warmed by the Gulf Stream, so that the warm waters that were coming up from the equator were flowing off the coast of North America towards Northwest Europe, and that's what gives Europe our mild temperatures, makes it possible to live there in the wintertime. And this was another interesting idea. He applied this idea to the Mediterranean Sea, because he said in the Mediterranean you have evaporation happening at the surface, and that causes downward convection. You have denser salty water going down, and that should be flowing out, and that would be balanced by an inflow at the surface. And they did measurements and they confirmed this. So even though you could see that the inflow at Gibraltar was into the Mediterranean Sea, if you take a measurement down below, you could see very clearly that the flow at depth was going out of the Mediterranean Sea. Now, Kroll, on the other hand, was a clerk at the Scottish Geological Survey. And he has some interesting contributions as well. He calculated that there should be a 100,000-year glacial cycle due to orbital variations. Nowadays, we talk about the orbital forcing of the glacial cycles as due to Milankovitch, but Kroll was talking about this as well. Anyway, Kroll was a fan of the wind-driven ocean circulation. He thought absolutely that was what was the most important thing. And what he showed is, did a calculation. He showed that the expansion of the ocean that you get at low latitudes at the equator due to heating was insufficient to account for an overturning circulation. In fact, he claimed it would not drive any circulation at all because it wouldn't be able to overcome the effects of viscosity. But he also said that any theory of the ocean ought to be mathematical. It shouldn't just be descriptive. Okay? And that's where we're going to be coming in this thing. Now, in the late 1800s, some important things were going on in fluid mechanics and also in physics. So in physics, we had the Maxwell. Maxwell wrote down a dynamical theory of electromagnetic fields. This was a unification of electricity and magnetism, two things that were known to be separate, and Maxwell showed them to be two aspects of the same thing. Very, very influential thing, and a lot of people are very excited about that. So this is a great time in physics. At the same time, there was one of the first great books on fluid mechanics by Lamb, the Treatise on Mathematical Theory of the Motion of Fluids. This is smaller scale phenomenon, but also using mathematics to explain fluid mechanics, so explaining that. Now, at the same time, meteorology and oceanography were seen as, quote, hobby sciences, like moth collecting or butterflies. It's not something that a serious scientist would do. If you were a serious scientist, you would do physics. You wouldn't do oceanography. Okay, that's when things started to change. So our first Scandinavian is Henrik Mohn. And like I said, none of these people really, it'll come later, but none of them started out as oceanographers. Usually they switched after doing something else. Mohn started studying theology, so he was interested in religion, but then he made a jump to physics and astronomy, and then finally switched to meteorology. And he wrote a book, an important book, back in 1863 about storms over the Nordic seas and also over Norway. Another recurring theme we're going to have here is that he founded the Norwegian Meteorological Institute, and he was its first director. So we'll see lots of connections with them as well. But so Mohn was the first one to start that, and he published a text on meteorology. So 1875. So we're talking about the same time as these other texts were coming out. So an early text on this. One of Mohn's ideas was something that he called the theory of baric winds. And baric winds is something we now refer to as geostrophic balance. So when you have a pressure field that the winds are aligned with the isobars of pressure. So you have a balance that goes on between the pressure gradients and the Coriolis force. And that means that when you have a map, like the map that I'm showing here, this is the surface pressure chart from yesterday. I just loaded this in. And if you ignore the fronts here, because that's a little more complicated, we won't get into that. But if you just look at these contours, these are pressure contours. There's a low pressure over the Nordic seas right now, centered over Iceland. Poor Iceland always gets walloped by, it's like a low pressure magnet. But anyway, there's a low pressure system that's there. And you see that when you have these contours, it means that if you're looking at the pressure contours, you're also looking at the winds. This is the direction that the winds are going. And the more tightly spaced those contours are, the stronger the winds are as well. Here we are over here, here's Oslo, and you can see this is a high pressure system. That's why we have this fantastic weather right now, because high pressure systems means clear skies and sunny and everything else. Okay, so Mohn developed this in particular, these ideas, into developing one of the early theories of cyclone formation. And what he said was that cyclones form when you have warm and cold air masses meeting. And this often occurs. So if you're observing, as we are from Scandinavia, what you often see is that these cyclones form off of Newfoundland, off the east coast of North America. And that's exactly what Mohn said, is that it's the boundary between cold and warm air. Okay, but Mohn also applied these ideas to the ocean. And this is something I really appreciate too, that the same ideas which were working in the atmosphere, these flow along isobars geostrophic balance, works just as well in the ocean. He was involved with an expedition in the North Atlantic, so he led the Norwegian North Atlantic expedition, so this is a sailing expedition, and he mapped the circulation in the Nordic seas, and again, putting these pressure contours to describe where the flow was going. So this is one of the early examples of a map of geostrophic flow. You'll see in a minute that this same picture holds today largely, this flow along the Norwegian coast and also flow along Greenland. But in addition, Mohn had a theory of transpolar drift, so that the ice in the Arctic should be drifting from Russia towards Greenland. And the reason why he came to this conclusion is there was a ship that was disabled, frozen into the ice, and that was carried across the Arctic. And so he said that he thought that it was probably wind-driven drift across the Arctic. So, and this is what prompted Nansen's expedition, which we're going to come back to in a minute. Okay, now we come to this person. This is Bjerknes, which is a perfect person to talk about since we're standing here in Bjerknes Hus. And after reading about Willem Bjerknes, I can say he absolutely deserved everything, every accolade he's gotten here. Absolutely amazing. Bjerknes was a son and an assistant to Carl Anton Bjerknes, who was a physicist. So he was exposed to science very early on. But after growing up, he went to Germany and he worked with Hertz on electromagnetism. So he developed his ideas initially studying electromagnetism, and that influenced his thinking. When he came back, he became a professor of mechanics at the University of Stockholm, and then subsequently moved to UIO, University of Oslo, back to the University of Leipzig, and then he went to Bergen and founded the Geophysical Institute in Bergen. Okay, even if he had just done those things, that would have been remarkable, but he did a lot more. He, for one, he has work in electromagnetism, so he derived a theory of electric resonance, so in particular how you can induce oscillations, for instance, in a metal using magnetic fields. He wrote down something that we now refer to as the primitive equations. So these are the equations that we use when we're doing weather forecasting or modeling the ocean. He described acoustic forces on bubbles. Okay, there are people that are very interested in how bubbles, and those forces are now known as Bjerknes forces. So if you study acoustics, then you probably know about Bjerknes through the bubbles. He talked about Bjerknes circulation theorem, which is something I'll show you in a second, a very important idea in our fields. And he was so well known that he even has craters named after him on Moon and also on Mars. So if you ever take a trip to the Moon on a SpaceX expedition, for example, you can go visit the Bjerknes crater. That's there. All right. This is Bjerknes circulation theorem, and I just want to give a quick, this is about the only math I'm going to show on this talk, so don't be afraid. The circulation theorem has to do with flow around a circuit. Okay, and again, you're going to see that the influence of electromagnetism is definitely there. This is a circuit, is what we would think of as for electricity, but you can also think of it as flow. So if we have flow around a contour like this, and it's a closed contour, then that flow, the component of the velocity around that circuit, is what we call the circulation. Now, if you think about a cyclone in the atmosphere, a low pressure system, you can have a closed contour around the center of that low pressure system. You can talk about the winds, for instance, a hurricane as well. They all have circulation. And of course, we're very interested in how that circulation changes. Is the hurricane going to become more intense or not? Now, there's a theorem that goes back to 1867 for barotropic flow. That's flow, roughly speaking, that has a constant density. So a fluid with a constant density is something you would see in a laboratory. And Kelvin said that if there's no forcing, no friction, then the circulation does not change. It's conserved. So very, very important idea. We teach this in our introductory classes. Bjerknes generalized this to a baroclinic flow, which is what we have in the atmosphere and the ocean, when you have different densities at different levels. And what he showed is that the circulation in that case can change if the density and the pressure surfaces aren't the same. So if there are differences between them, then you can generate circulation. Now, how would that work out? So here's an application. This is from his paper in 1898 describing sea breeze. All right, so sea breeze, if you haven't experienced it before, if you are near the coast, you have a cabin near the coast, and as the land warms up, there's a contrast between the colder ocean and the warmer land, and you develop a flow. Okay. Well, what happens is if you look at this, these dash contours that he's drawing are pressure surfaces, and the contours, the solid contours, are density contours, and they're not the same. Out here they are, so offshore they're the same, but as you come in towards land and you have this heating, then you have the density contours bending down. So there's a region here where they're not the same, and that generates circulation. So it's what Bjerknes referred to as a solenoid, which is again something you would talk about in electromagnetism. So the generation of solenoids. But this is the first realization that you could get this kind of flow forming from density contrasts. Anyway, he also applied, so Bjerknes, like Mohn, applied the idea to the ocean as well. So he just flipped it upside down. He said, if you have a region, for instance, where these density contours are sloping up to the surface, then you can have a flow in the ocean as well. And that's something we now refer to as coastal upwelling. So Bjerknes used these same ideas to explain how that could happen. Okay. Now, next one I'm going to mention here is Bjørn Helland-Hansen. And again, coming from a wide range of backgrounds, Helland-Hansen was going to become a doctor. So he was studying medicine here at the University of Oslo. But he was in Finnmark on an expedition, and he got frostbite on his hand, so he lost several fingers. So that was it for medicine for him. He was not going to be a surgeon with only a half a set of fingers. So what he did is he switched to marine science, okay? Medicine's loss and our gain. What he did was he mapped the Nordic seas. He's an observationalist. He mapped the Nordic seas, working with Fridtjof Nansen, who I'll come back to. And he was an assistant to Bjerknes. So Bjerknes was his inspiration, and he used some of Bjerknes's ideas and applied them to the ocean. For example, he simplified the circulation theorem that Bjerknes had, and to apply it specifically to the ocean. He did other things as well. He developed a photometer. So if you study optics in the ocean, this is something that you know about. It's called the Helland-Hansen photometer. He developed that, and he became the director of the Geophysical Institute in Bergen. So again, another after Mohn. Here's a picture of the map that they made of the Nordic Sea. So this is from Helland-Hansen and Nansen in 1909, and it's on the left-hand side here. And it looks a bit like what Mohn had drawn using his pressure surface. As you see, there's the inflow coming in. This is what we now know as the Norwegian current. That splits. Some of it goes up towards Svalbard, while the rest of it is going into the Barents Sea and circulating in the Barents Sea here. Up towards the Fram Strait, and then the surface currents are coming back along the coast of Greenland. It's now known as the East Greenland Current, and flowing out through the Denmark Straits. So, and this picture is largely correct. So here we are almost 100 years later. This is another Norwegian oceanographer, Cecilia Moritzen. This is her thesis work from 1996. And Cecilia was essentially making a three-dimensional version of that figure, talking about where the sinking was happening and about that. And so, but you see the same features: the Norwegian current, the splitting into the Barents Sea, flowing up around Spitsbergen, and then this deep flow as becoming denser off of Spitsbergen, going into the Arctic, and then recirculating and flowing out at depth. That now becomes the North Atlantic deep water, which is among the densest water in the world ocean. That flows out here. This is why the Nordic seas are such an important part of the whole global ocean, because this transformation that happens in the overturning circulation. But anyway, here we are, 1909, and this is 90 years later, and you see how they're very similar. Okay, another one on my brief tour here through Scandinavian contributions is a person named Johan Sandström. And I'm saying Scandinavian because, not just Norwegian, because we have some very important Swedish scientists too, and there was a lot of interaction between these two places. Of course, Norway was part of Sweden back then as well. Sandström was the son of a carpenter in northern Sweden, and he worked in a mill to support the family. The hope was, his father hoped, that he would take over the mill and become the head carpenter. But he had something else happened. He met Willem Bjerknes. So in 1899, he became an assistant to Bjerknes, and that changed his whole trajectory. I don't know what happened to his carpentry mill. But anyway, I do know what he did after that. He studied atmospheric circulation, but particularly became interested in oceanic phenomenon. And this is one of the great ironies. I mean, there's lots of ironies in science, but this is one of them, that he believed the winds were much less important for driving the ocean than density. He thought density was the major driving force for the ocean. Ironically, we now remember him for proving what most people interpret as the exact opposite. So that comes from here. This is Sandström's theorem, 1908. This has to do with convection. When you're in the atmosphere, so if Z equals 0 is here, the sun is shining and warming up the surface. And that makes the surface, particularly land, warmer than the overlying air. So you get convection. So this is where clouds come from, and the air rises. And at the higher levels, the colder air has to descend to replace the air that's welling up. Okay, and this is known now as Rayleigh-Bernard convection. And again, there's something that was studied in the laboratory in the 1800s, and it's very well known in fluid mechanics. Lots of theorems about this. Okay. What Sandström did in 1908 is he said, okay, what happens in the ocean? In the ocean, the heating is happening at the top, not the bottom. And the cooling is also happening at the top and not the bottom. And so he had a theorem, and what he said was that if the mixing in the ocean, so in the small scale mixing in the ocean goes to 0, so if you have very weak mixing, then this density-driven circulation becomes trapped in a very thin layer at the top of the ocean. And so as the mixing goes to 0, it's a vanishingly thin one. So you basically have a uniform temperature at depth, and then you have this sharp change up at the surface. All right. Now, later on, there was an article by Jeffries in 1925 saying essentially this is not relevant for the ocean. Mixing is important in the ocean, so this is not. But most people nowadays, when they talk about Sandström's theorem, and I've heard this myself, saying, you know, when you're talking about thermally driven ocean circulation, well, according to Sandström, that doesn't happen. So like I said, Sandström believed it was important and proved the opposite. Okay. But anyway, we still definitely talk about this theorem. Okay. Here's another person that's very well known around here. This is Fridtjof Nansen, and what a character he is too. Nansen studied zoology at the University of Oslo and did some early work, important work on the neuron. So remember, we had a seminar here a few years ago where neuroscientists were talking about his contributions in that. So not so significant contributions there. But he was also a real athlete. I remember reading his diary 30 years ago and talking about some of the skiing he did. When he was 18, he broke the world 1 mile speed record, 1.6 kilometers. He was the fastest in the world at that point. He also traversed Greenland on skis, and he was nearly the first to reach the North Pole, also on skis. So just superhuman. Contribution to oceanography, he mapped the Nordic seas with Helland-Hansen. He invented something that we now call the Nansen bottle, which is a device that's lowered from a ship, a bottle. It flips over and then captures water at depth, and then you pull it back up, and then you can measure the temperature and the salinity of the subsurface water, so widely used. But in addition, he won the Nobel Prize, and not for oceanography or for medicine. He won it for humanitarian work. So he won the Nobel Peace Prize for his work on behalf of refugees. He was the UN High Ambassador for Refugees. Amazing. Okay. Anyway, the part that's important for us in oceanography is his expedition to the North Pole. And he was intrigued by Mohn's idea about transpolar drift. So he thought, okay, wait a minute. If that ship, which broke down, drifted across the Arctic in the ice, I could freeze my ship into the ice and drift across and then be the first one to the North Pole. Perfect. So he sailed up, had a ship designed. This is the Fram. Most everyone knows about it, but if you don't, then you need to go down to the Fram Museum in Oslo and then read all the stories on the side of the wall and also see the ship, because it's absolutely amazing. He designed the ship so that it wouldn't be destroyed by the ice as it froze in. On this expedition, he made a number of important observations, which I'll mention. And then, like I said, when he realized that he was not going to reach the pole, he got off the ship, put on a pair of skis with a colleague of his, and they tried to ski in. It seems insane right now, but they actually survived, and they got back to Oslo. I mean, they had to ski back again. They didn't make it, but they did get picked up by a fishing boat. They arrived in Oslo, I think, the day before the Fram got back. All right, these things it's just amazing. Okay, 2 important observations, though, as far as oceanography goes. The first one is something that we now refer to as dead water. And what he found is that the Fram, as it was steaming along, would get into situations where with totally flat surface, but then it had a very difficult time moving, almost as if it were in molasses. So the ship was really struggling to make any progress at all. So he said in calm weather, with light cargo, they could go 6 or 7 knots, 7 nautical miles an hour. But in this dead water, they could only go 1.5 knots. So very puzzling. But he had some ideas about what was going on, but he didn't solve it, but he just had some intuition. Very, very good intuition as a scientist. Nansen also noticed, this is on the right, this is something I talk about in one of my courses in the fall all the time. Nansen noticed that when, let's say if the wind is blowing away from me towards you, that the ice did not go with the winds. The ice drifted off to the right. And it's typically 20 to 40 degrees off to the right, consistently off to the right. He realized that the Coriolis effect probably had something to do with this. So the rotation of the Earth was probably important. And he had some ideas about what was happening in different layers. But again, he wasn't able to solve that problem. He just had ideas about how it should be working. Okay, that brings us to our next example. This is, now I'm not sure how you pronounce this, Vagn Walfrid Ekman. And Ekman, so he was studying physics at Uppsala University, so in Sweden, but he switched over to oceanography. And why did he do that? He heard a lecture by Bjerknes. Okay, so he heard Bjerknes, and that completely changed his whole trajectory. And he then became a graduate student working for Bjerknes. And this is what made his career. But in addition, so I've got some other things here, but in addition, I point out, because I'm also a musician, he was an accomplished bass singer. I don't think many people know this, a pianist and a composer. So he wrote music as well. Interesting character. Okay, so Nansen was talking with Bjerknes and telling him about these two strange things he had seen: dead water and also the ice drifting in the wrong direction. Bjerknes said, I've got a pretty good graduate student. I'll put him on it, right? And so they had ideas about what it was, but they put Ekman on it. So Ekman did some laboratory experiments, and here's a picture over here underneath. The top is a picture from a ship of when you have this calm water and this difficulty of moving the ship. And then this is the experiment that Ekman did. And so what he did was he had two layers. So you had a lower, this is the ocean, and the top layer is fresh water. So it's a cap of fresh water on the top. And what they realized is that the ship could generate waves on the interface between the fresh water and the deeper water. And that, of course, takes energy. That interface happens everywhere in the ocean. They're called internal waves now. The amplitudes can be enormous. They can be 100 meters high. But to generate that, it takes quite a bit of energy. So the ship was doing this. It was not generating waves at the surface. It was making major waves below the surface, and that took energy. So that described what was the dead water, that solved the whole dead water phenomenon. The other thing I just mentioned I have here too is that this is something Benjamin Franklin had also, back in 1762, described these internal waves as well. So Benjamin Franklin, one of my heroes, American scientist, talked about this as well. So for instance, if you have water over oil, it's very easy to see, and you can see that you have these waves on that interface. Okay, but here's the one that's for oceanography was a big one. This came out in 1905. Ekman wrote a paper called On the Influence of the Earth's Rotation on Ocean Currents. 1905 was the great year for Einstein when he published on special relativity, the photoelectric effect, and the Brownian motion. But this paper in 1905 was more influential. So Bjerknes again suggested to Ekman, who was just a student, he said, why don't you look at Nansen's ice drift problem? And Ekman developed a theory. So as simple as possible, using Einstein's dictum, you use the simplest possible model, but not too simple. He did this, so winds forcing the surface with some sort of mixing that's happening below the surface. And this model exhibits exactly the same type of behavior. So it's shown on here on the right. If the wind blows to the north here, the surface velocities are off 45 degrees to the right. In a realistic ocean, it'd be somewhat less than that. 20 to 40 is about right, but 45 is pretty good for such a simple model. But then interestingly, what happens is below the surface, so if you go down, the velocities turn and they weaken with depth. So you get this structure, this very beautiful shell-like structure, which is now known as an Ekman spiral. And you can see how it turns. So at some point, the velocities are actually even in the opposite direction to the winds if you go down deep enough. And if you integrate over this, so just to see what the net motion is from the surface all the way down, the velocity is 90 degrees to the right of the current. Okay, that's something we now call the Ekman transport. So all of this, Ekman has his name, all of this. I always say this to my students, this is an important lesson. Make sure you get a good advisor who gives you good problems like this, because now we have Ekman all over the field. Okay, I got to keep moving here. All right. Okay. So what happened after 1910? That was really the high point. At that point, Scandinavia was the center of the universe when it came to meteorological and oceanographic research. everybody came here. So people who were studying in Germany and Canada and England, they all came over to study over here because they wanted to learn from Willem Bjerknes and all his proteges. But thereafter, what happened is the research shifted abroad, and but it was often done by Scandinavians who were living abroad. So I'll give you some examples. This is another one who has his name on our field. This is Carl-Gustaf Rossby, who was a Swedish scientist. So he also came from physics and converted to meteorology after meeting, guess who? Willem Bjerknes in Bergen. But after that, he moved to the United States. He became a professor at MIT, where I studied. He's then was a research associate at the Woods Hole Oceanographic Institution, where I'm an adjunct scientist. And then he went to the University of Chicago. And after that, he went back and forth between Sweden and the United States. He was a big fan of atmospheric chemistry, which is something that people in my group really love. And he showed how CO2 could actually warm the atmosphere, so increasing CO2 concentrations. And if you're taking one of those SpaceX missions and you're going to Mars this time to visit the Bjerknes crater, you'll also see the Rossby crater, because he has a crater named after him on Mars as well. Okay, I'm going to skip that, but I'll mention Rossby waves. So this, again, one of the many ideas that he had which were very influential. If you look at a weather map, you see that the jet stream meanders like this, very typically. And this wave-like meandering is something we now refer to as Rossby waves. And these exist, Rossby showed this, because the Coriolis, the effect that rotation has, varies with latitude. All right, so you have a weak effect at the equator, a very strong effect at the pole, and that gradient, that change in the Coriolis effect, allows for waves. This is a fundamental dynamical element that we now use for understanding the atmosphere, but also in the ocean. So if you look in the ocean, you look at satellite measurements like this, satellites now can measure the deviations of the sea surface height down to the centimeter level. And what you see when you look at this is large-scale structures propagating westward across the ocean, moving at different speeds, and the speeds are exactly in line with what we expect for Rossby waves. So these Rossby waves are also very important in the ocean, and they're thought to mediate changes in the climatic state of the ocean. Okay. I also want to mention this person. Okay, I'm running out of time here, but all right. This is another important one. He studied realfag, so he studied natural sciences here at the University of Oslo. He was, of course, a student of Willem Bjerknes, and was a chair of meteorology at the University of Bergen, but then he became the director of the Scripps Institution of Oceanography, which is where I was in it's big ocean. I think it's the biggest one now, or at least one of the two with Woods Hole in the world. And he was a very, very influential director back in the 1930s and 40s. So really, he designed their whole educational program. Sverdrup's idea, which again is very, very important in oceanography, is that if you take Ekman's ideas, so if you have the winds blowing, for example, here westerlies and easterlies, and you look at how the Ekman transport can give you convergent motion, for example, that can drive large-scale gyres. And he derived a simple relationship to show this. This is now known as the Sverdrup balance, or Sverdrup relation, and these structures are called Sverdrup gyres, right? And these gyres are actually in very close agreement with what we observe in the ocean. So the wind-driven circulation is very well described by these large-scale gyres, which with the name of Sverdrup on them. So it's really one of the great successes of a simple theory explaining more complicated dynamics. Sverdrup also wrote one of the first great textbooks in oceanography, because they didn't have one back then when he was a director at Scripps. So he, together with Johnson and Fleming, wrote a book on the physics, the chemistry, and the biology of the oceans. It was called The Oceans, and it was the standard text for many years. Okay. I'll just mention a couple other Scandinavians here quickly. There's many more, but Arndt Eliasson, who was a professor of dynamical meteorology in our department, who developed something called the quasi-geostrophic system. He was working in the 50s and the 60s and the 70s. And that's a system that we still use today when we're teaching dynamics in the atmosphere and the ocean. And this fellow over here, Ragnar Fjørtoft, who was the director of the Meteorological Institute, but developed ideas on stability, but also on something that's now known as the inverse cascade of energy in a turbulent system. So these ideas are important not just in our fields, but also in fluid mechanics. Okay. All right. Okay, I'm running out of time here, but I just wanted to make a few comments just to sort of sum up on all of this. Okay. So what was the key ingredient in the development of these dynamical fields? Well, physics was, right? All these people were getting inspiration from physics. Half of them started out as physicists and then switched over. And following the Einstein idea, they developed simplified mathematical models like Ekman to capture these phenomena. So very, very important. And this is what we use now when we're teaching these fields. What they did was they converted meteorology and oceanography from this hobby science into something predictive, into a real quantitative science. And so that was an incredible thing. I often feel like I'm defending this, but because the question is, do we still need simple physical models like this? And believe it or not, we have to argue for this. And yes, and I think the answer is yes, many of these phenomena are still unexplained. For example, what drives the meridional overturning circulation? We still have people saying it's winds, and we still have people saying it's density contrast. So this is 150 years after Carpenter and Kroll were tearing each other's hair out. We're still debating the same thing. But simplified models, so they can be used for helping to understand our more complex climate models, but in addition, they can actually, in some cases, be used for prediction. So for instance, predicting the currents out in the Nordic seas. So they're extremely valuable. Now, why is Scandinavia? Why is Scandinavia such a center of action? And I think a lot of it has to do, for oceanography anyway, has to do with the deep connection to the ocean here. You had the Vikings who were sailing, you have fishing, a lot of the oceanography, physical oceanography was for informing the biologist about where upwelling was happening, what was happening to fish populations, that sort of thing. So very, very tight relationship between Scandinavia and the ocean, and that had a huge impact. Why did it flourish here? The answer is it's the guy who has this place. I'm almost done. It's Willem Bjerknes. And you see this in a lot of fields when you have somebody who is a central figure who inspires a lot of other people. All of these people, Helland-Hansen, Ekman, Mohn, Sandström, Sverdrup, Rossby, Nansen, were influenced by Bjerknes. So Bjerknes his great contributions were not just the science that he did, but the science that he inspired. It was really remarkable. We still have a deep impression of Scandinavian legacy on our language. We have the Bjerknes circulation theorem, but we have the Ekman spiral, Ekman layer, Ekman transport, Ekman pumping. We have the Sverdrup balance, Sverdrup transport, Sverdrup stream function. I wrote a paper on Sverdrup discontinuities. We have Rossby waves, Rossby radius of deformation. We have Elias and palm fluxes, and we have the Fjørtoft stability criterion. So it's the influence is written on our field. Now the question, and what about this though? Can we still, the heyday of Scandinavian oceanography was 100 years ago. Can we be great again? And the answer is yes, but we need to learn from what happened in those early days. You need to have a nucleus of activity. You need to have these central people who are inspiring others to do that. But you also need to fund basic research. And I think this is something that a lot of us feel very passionately about, that basic research is extremely important for doing this. Okay. Here are some sources. If you're interested in reading any more about this, there's a great book called Fluid Envelope of the Planet. Adrian Gill's book on atmosphere ocean dynamics has lots of history. It's absolutely fascinating. A lot of this you can get on Wikipedia. So if you just go to Wikipedia and cruise around there, you're going to get lots of information. And I got good comments from Cecilia Moritz and also Robert Mark Friedman, who's here at the university. And lastly, there's a song that was written about the Ekman spiral. That's in Norwegian, so I won't do this. But this was written in 1968 by our colleague Ivan Os, who passed away last fall. But just another example of how influential Ekman and all the Scandinavians were to our field. Thanks.
Thanks. Thanks a lot, Joe. That was a wonderful, exciting survey, especially through the Scandinavian background of physical oceanography.
great.
Thanks so much.
Yep.
We got a few questions.
Okay. Oh, yeah.
Yeah,
Okay.
so
all
I
right.
just will ask them to you.
Okay, fine. Yeah.
Edina had some good questions.
Okay.
How did Mohn and company do mapping of circulation in the Atlantic? And what kind of instruments did they use?
Yeah.
What did they measure? And how long was such an expedition at that time?
Okay, that's a good question. Again, you have to think that you're on a sailboat. So how are you measuring subsurface currents? Usually it was done by lowering a weight over the side of the boat and looking at the deflection of the weight. So this is what they did in, for instance, in the Mediterranean Sea when they were looking at the outflow from that. You lowered a weight, you saw how far it was deflected, and then you could figure out roughly how fast it was going. So painstaking work, but that's the type of measurements that they were
Do you know how long was the expedition at that time?
The expeditions, which one? Mohn's expedition in particular?
Yeah.
I don't remember. But these expeditions were of varying length. Some of these British expeditions that I mentioned went on for years. So they would just sail and sail and sail. Humboldt, that was a multi-year endeavor as well. So it took a long time. Sailboats are not fast. You have to go at that speed.
There was another question by
Yep.
Chi-Hong. She
Yeah.
is asking, so now you showed us the competition between the wind-driven versus the density-driven.
Yeah.
Is that now solved nowadays? And I know
No.
there's even a third component coming in.
Yeah.
Can you say something just to comment what is the current knowledge?
Yeah.
Who's winning?
Yeah. So when you talk about, for example, when I show this picture of the wind-driven gyres here, there are aspects of this that we don't understand, but the large-scale structure is pretty well described by the Sverdrup gyres. So these ideas are pretty good. I should get closer to the microphone. Okay. So the general structure that you see here, for example, in the Pacific, where you have the flow going eastward in the Kuroshio and returning westward below, and then happening over here too, connected by these western boundary currents. This was something I didn't talk about, but this was an American contribution by Henry Stommel. But the general characteristics of these things are correct. When you talk about the overturning circulation, though, that is absolutely under debate. So we still are discussing to what extent it's buoyancy driven. People that reject that using Sandström's theorem and claim that the winds are more important. Some people say that the winds around Antarctica are important in driving the overturning circulation. So there's lots of different ideas.
But what about the eddy driven part? You haven't.
So the eddy, I think that what eddies are doing is that they're modifying. For example, they modify these western boundary currents. Okay, they're important for doing that. They are important for fluxing heat across some of these currents as well. And they have a big role down in the south. In the Southern Ocean, the Antarctic circumpolar current, it's important down there as well. But I think by and large, the main driving things are the winds and the large-scale density contrast. Those are the really important parts. Yeah.
Thank you so much.
Okay.
And yes, I think we will finish for
Finish
today.
there? Okay.
Thanks for all of you of joining. I heard we had over 90
Good.
participants.
Oh,
so
good. Yeah.
Record.
Okay.
Thank you.
Yeah. All right.